Welcome to the deep dive. Today we are embarking on, well, perhaps the grandest journey we've ever attempted here.
It's a big one.
Our source materials, this huge stack of physics, philosophy, history, they really demand we confront the biggest questions out there.
Like, where did everything come from? Where is it all heading?
And maybe most importantly, what's the point? What's the meaning of, the few moments we actually get in between all that?
It's a deep dive, all right. Powered by science, definitely charting the cosmos.
But it's all framed by us, by humans. Our ability to make sense of it through story, consciousness, art.
And that brings us straight to the ultimate tension, doesn't it? It defines everything we're going to talk about today.
Okay.
The sources, they lay out this profound split in the human experience. On one hand, we're searching for the timeless, the absolute. You find that in math and physics, right? These elegant, unchanging laws.
Constant.
Exactly. But on the other hand, we are, well, uniquely aware of our own mortality. Oswald Spengler pointed this out centuries ago. Man is the only being that knows death.
And that knowledge, that pressure, that's the engine.
That's what fuels everything. All our science, our religion, our philosophy, it all stems from knowing we have an end.
Which creates what Ernest Becker called the existential tension. That feeling of being pulled in two directions.
Pulled upwards, yeah, towards the infinite sky. By our minds, we can write symphonies, figure out the universe.
But we're stuck here, tethered to this physical body that's gonna, well, decay, turn back to dust.
Precisely. And to understand how we even try to bridge that gap, we first have to get our heads around the basic rules of the universe, the cosmological framework.
So our story starts with these two huge fundamental forces choreographing everything.
Entropy and evolution.
Okay, let's unpack this. Starting with the bedrock of the physical universe.
Right, and our grasp of the universe's fate, funnily enough, it kicks off somewhere really practical, the steam engine.
Seems a bit industrial for cosmology.
Well, back in 1824, Sadi Carnot was studying how efficient these things were. He wasn't just trying to get more power out of them.
He was accidentally launching thermodynamics.
Exactly. The study of energy, how it converts, and, crucially, how much gets wasted.
Because the steam engine is kind of the perfect template for entropy, isn't it?
It really is. You take high-quality, ordered energy-burning fuel, say, and turn it into useful work, motion.
But it's never 100% efficient. A huge chunk just gets lost as low-quality waste heat, useless warmth.
And that inevitable path towards degradation through its useless energy, that's basically entropy increasing.
Which leads to this really strange paradox in physics, doesn't it?
Oh yeah, it's a big one. If you look at the fundamental laws, Newton's, Maxwell's, Einstein's, they don't care about time's direction.
Or time symmetric.
Right, mathematically, if something can happen forwards, the reverse should also be possible.
But that just feels wrong in day-to-day life. I drop a glass, it shatters. The laws allow that.
Of course.
But the reverse, all those little pieces spontaneously flying back together into a perfect glass, the math allows it, but...
It just never, ever happens. So why the disconnect?
Okay, yeah, why?
This is where it gets really interesting. We move from absolute laws to statistics. Irreversibility isn't some hard rule from physics. It's about probability. It comes down to microstates and macrostates. Thanks, Boltzmann.
Okay, define those for us. Microstate versus macrostate.
A microstate is the exact arrangement of every single particle. Its precise position, its speed, everything. Super specific.
Got it.
The macrostate is just the overall appearance, what you actually see, like the gas fills the room or the glass is shattered.
So entropy. It's the number of different microstates that result in the same macrostate.
Bingo. It's not just messiness. It's the number of ways something can be messy or arranged in a certain general way.
Okay. Let's use that penny analogy, the 100 pennies.
Good one. The macrostate all heads, that's very ordered, low entropy. And there's only one way for that to happen, right? One specific microstate.
Only one.
But the macrostate, 50 heads, 50 tails, looks totally random, high entropy. But how many ways can that happen?
An absolutely enormous number. The sources say something like 10 to the power of 29 ways.
Roughly, yeah.
Yeah.
Ale1 followed by 29 zeros. Just astronomically more likely than all heads.
So the difference is staggering. High entropy states, the messy ones, are just vastly, vastly more probable because there are so many more ways for them to occur.
They're typical. They're easy. That's the default state for things.
It's like steam filling a bathroom. If you walk in and the steam is just spread out evenly, high entropy, you don't think twice.
Exactly. But if you walked in and all that steam had somehow gathered itself into a perfect little cube hovering in the corner.
Low entropy! You'd know something was up. Something weird happened. It wasn't just chance.
Right. That requires some kind of intervention, some organizing force. It doesn't happen spontaneously.
And this statistical reality, this overwhelming tendency towards high entropy states, is why the future looks different from the past.
The future is almost certainly going to be more disordered, have higher entropy, lower quality energy, more spread out.
And while the laws don't technically forbid entropy decreasing for a moment,
Like our steam cube.
for anything bigger than a few atoms, it's just so ridiculously unlikely it might as well be impossible. Burnt toast isn't going to uncook itself.
Not in this universe, anyway. That's the practical reality the second law imposes.
Okay, so there's this relentless push towards disorder, towards things falling apart. But look around. We see stars, galaxies, planets, us. Incredible order. How?
Doesn't that seem like a direct violation of the rule we just talked about?
It really does. How do you get order if entropy must increase?
It's the great cosmic balancing act. The sources call it the entropic two-step.
Okay.
The key is total entropy in the universe always goes up. But you can create pockets of local order, decrease entropy here, as long as you create an even bigger mess, a larger increase in entropy over there.
So you pay an entropy tax to the surroundings?
A massive one. And this is where gravity comes in. Surprisingly.
So it's the weakest force, isn't it?
By far. But it has a unique property. It only attracts. It's
Yeah.
purely cumulative.
So over cosmic distances and massive scales.
It wins. It dominates. Now, picture a huge spread out cloud of gas, mostly hydrogen, floating in space.
Okay. Diffuse gas. High entropy, you'd think. Should spread out more.
Intuition says yes, but gravity says no. It starts pulling that gas cloud inwards. The center begins to collapse.
And this collapse does something weird thermodynamically.
Totally weird. Unlike your coffee cup, which cools down when it loses heat to the room,
Right.
this collapsing gas cloud has what's called negative heat capacity. As gravity crushes the core, its volume shrinks and its temperature skyrockets.
Okay, core gets smaller and hotter. What about the outer parts?
The outer shell actually expands and gets cooler. Volume increases, temperature drops.
Wait, so you have a super hot core next to a cooler shell. Heat should flow outwards, right?
It does, but here's the paradox. When the hot core radiates heat to the cooler shell,
The core gets even hotter and the shell gets even cooler. That's backwards.
it's completely absurd for coffee, but it's true for massive gas clouds when gravity is running the show. It's a runaway process.
A self-amplifying cycle. The core shrinks faster, gets hotter faster, radiates more.
Making the shell expand and cool faster, which allows the core to keep collapsing and heating until, boom, about 10 million degrees.
Ignition. Nuclear fusion kicks in.
And that's the final step. Fusion itself, turning hydrogen into helium, seems like creating order, right? Making more complex stuff.
Yeah, simple atoms become more complex ones. Lower internal entropy.
It is lower internal entropy.
Mhm.
But to achieve that, the fusion process unleashes this absolutely enormous flood of high-energy photons, light and heat, low-entropy energy.
Which blasts out into the cold, empty space.
Exactly. That radiation spreading out into the vastness represents a huge increase in the overall entropy of the universe.
Yeah.
Far bigger than the decrease inside the star.
So the star pays its entropy tax. It achieves stability and internal order.
By aggressively exporting disorder, spraying low-entropy sunlight out for billions of years.
Got it. Gravity crushes, the nuclear force fuses and radiates. Together, they create stable structures like our sun, which are basically entropy-generating machines.
That's the entropic two-step in action. Creating local order by paying a massive entropic price elsewhere.
Okay, so that's sunlight, that low entropy energy pouring out from stars, showers planets like Earth. And that energy is what allows for the next big jump in complexity, life.
But before life could get started, you needed the right ingredients, right? The cosmic pantry had to be stocked.
We needed the basics. Carbon, hydrogen, oxygen. Stuff we're made of.
The SPONCH elements, as biologists sometimes call them, sulfur, phosphorus, oxygen, nitrogen, carbon, hydrogen. And where they came from is this amazing cosmic story.
Okay, hydrogen and helium are easy, relatively speaking. Cooked up right after the Big Bang.
In those first few minutes, yeah. Gamow and Alpher figured that out. The universe was hot and dense enough to fuse the simplest elements, and we see the predicted amounts everywhere we look.
But what about carbon, oxygen, iron, the heavier stuff?
For those, you had to wait for the first stars to form, live, and die. People like Eddington, and later Fred Hoyle, realized that the centers of massive stars are like cosmic pressure cookers.
Forging heavier elements through fusion.
Exactly. Intense heat and pressure smashing lighter nuclei together to make heavier ones. Carbon, oxygen, all the way up to iron.
So the atoms that make up this planet and us, They were literally made inside stars billions of years ago.
Forged in stellar furnaces, absolutely.
Right.
And then when those massive stars reach the end of their lives,
Supernova.
or other kinds of stellar explosions or collisions, they blast these newly minted heavy elements back out into space.
Seeding the next generation.
Precisely. That enriched dust and gas mixes with other clouds, collapses again, and forms new stars and planets.
Yeah.
Our sun isn't a first-generation star. It's maybe a third generation, a grandchild star.
Made from the ashes of long-dead stars. We are literally stardust.
Quite literally. So this material eventually formed Earth about 4.5 billion years ago. Now, what was early Earth like? The Hadean period.
Usually pictured as this hellish landscape, right? And
Yeah.
molten rock, volcanoes everywhere.
That was the old view. But the geological evidence, particularly these tiny, incredibly tough zircon crystals,
Found in Australia, they're ancient.
some date back 4.4 billion years, just 100 million years after Earth formed. And their chemistry suggests something surprising,
What's that?
that Earth might have cooled down much faster than we thought. Quickly enough for liquid water oceans to form very early on.
So maybe less of an inferno, more of a water world with some islands.
Potentially, yeah. Still hostile, but maybe with oceans. And having liquid water is just critical.
Could be universal solvent.
Its molecular shape, that bent V shape, and the way the charge is distributed, slightly negative on the oxygen, slightly positive on the hydrogen,
Makes it polar.
which makes it fantastic at dissolving things, pulling apart salts, letting chemicals mix and react. It's life's varying fluid, absolutely essential for the kind of chemistry needed for life. Like carrying the ocean around inside us in a bag, as one scientist put it. Hashtag tag 2.2 molecular Darwinism and the universal mechanism of life.
Okay, we have the ingredients, we have the water. How do we get from just complex chemistry to, well, life? Self-replication, metabolism.
Now we're hitting the really big questions. Schrödinger asked it brilliantly. What makes a lump of matter alive? What's the difference between the atoms jiggling in a rock and the atoms in a rabbit?
It's not the atoms themselves or the laws they follow.
It's the organization. The rabbit has what the sources call an internal archive of information. It has software,
DNA.
the double helix. Watson and Crick's a periodic crystal. It's not repetitive like a normal crystal. Its sequence carries information. Instructions.
Instructions for building proteins, the workhorse molecules of the cell.
Exactly. Written in this code of three-letter words, codons, using just 4 chemical letters, A, T, G, C.
And remarkably, that genetic code is basically the same across all known life on Earth.
From bacteria to us, it's stunningly universal, which strongly suggests we all share a single common ancestor way back when.
Okay, so DNA provides the blueprint, but life needs energy. It needs to do things.
Right. And fundamentally, life runs on a kind of controlled chemical fire. It's called a reduction oxidation.
Electrons getting passed around.
Think of it like electrons cascading down a set of chemical stairs. Each step down releases a little burst of energy.
And life has figured out how to capture that energy instead of just letting it dissipate as heat.
Precisely.
Yeah.
It uses that energy often to pump protons, hydrogen ions across a membrane, like pumping water uphill behind a dam.
Building up pressure, a gradient, stored potential energy.
A massive electrochemical gradient. You get this huge buildup of protons on one side of the membrane.
And then?
Then, the cell allows those protons to flow back across the membrane down the gradient, but only through specific channels. And flowing through those channels turns these incredible molecular machines.
Tiny turbines.
Literally nanoscale rotary motors. And their spinning motion is used to stick a phosphate group onto a molecule called ADP, creating ATP adenosine triphosphate.
ATP, the universal energy currency of the cell.
It's like the charged up battery or the UPS truck, delivering energy wherever the cell needs to do work, build proteins, move things around, copy DNA.
And the scale of this is just mind-blowing.
Your body, right now, is synthesizing something like 10 to the power of 20 ATP molecules every second.
10 with 20 zeros after it per second, just to keep going.
It's a constant, furious hum of activity, all just to maintain order against the pull of entropy.
It's incredible, but how did this unbelievably complex system even start?
Yeah.
How do you get from simple chemicals to DNA, proton pumps, ATP?
Biogenesis.
Yeah.
The origin of life. That's the billion-dollar question, maybe trillion. The leading idea is molecular Darwinism.
Natural selection acting on chemicals
Yeah.
before actual life.
Exactly. Maybe simpler molecules came first. The RNA world hypothesis suggests RNA, which is simpler than DNA, might have acted as both the information carrier and the catalyst to get chemical reactions going. It could have kickstarted the process.
A simpler precursor system.
Possibly. And then there's this other really interesting idea from physicist Jeremy England, dissipative adaptation.
Okay, what's that?
England argues that, well, maybe lifelike properties, structures that get good at maintaining themselves, resisting internal disorder, even replicating, maybe these are just the expected outcome when you have a steady energy source,
Right.
like the sun.
Shining down on a bunch of competing chemicals for a long, long time.
Yeah. The structures that get really good at absorbing that energy and dissipating it efficiently, as heat basically, increasing entropy in the environment most effectively, those structures will tend to become more stable, more dominant.
And replication.
Replication, England suggests, might just be the best strategy for dissipating energy, a really potent tool for dissipative adaptation.
So in this view, life isn't some freak accident, but maybe a thermodynamically favored state. A really efficient way to turn sunlight into waste heat.
It's a provocative thought, isn't it, that we're essentially just very complex, highly optimized entropy-generating systems.
Okay, from the complexity of a single cell, we now leap to, arguably the most complex thing we know of, the human brain.
90 billion neurons, 100 trillion connections between them. The numbers are just astronomical.
It's the ultimate pocket of low entropy, isn't it? The most ordered structure for its size that we've found.
And out of that staggering complexity arises consciousness, subjective experience. Which brings us to what philosopher David Chalmers called the hard problem.
Right. We can map the neurons firing, the chemicals flowing, the data processing. That's the easy problem, relatively speaking.
We can trace the mechanics. But the hard problem is explaining why all that physical processing feels like something from the inside. Why is there what it's like to see red or feel joy or taste chocolate, the qualia?
The raw subjective feel, and the classic thought experiment here is Mary's room.
Ah, yes. Mary, the color scientist, locked in a black and white room her whole life. But she learns every single physical fact about color vision. Wavelengths, photoreceptors, neural pathways, everything.
She knows it all, scientifically. Then one day she walks out and sees a red apple for the first time. Does she learn something new?
That's the crux. If she learns something new, the actual experience of red, it suggests that physical facts alone don't capture all of reality. That consciousness is something extra, maybe non-physical.
But the physicalist counterargument is strong, too.
Very. The physicalist says no. Mary doesn't learn a new fact about the world. She gains a new ability. She gains the know-how to recognize red, imagine red, remember the sensation of red.
So the feeling itself is just part of the complex physical processing, a result of it, not separate from it.
Exactly. The subjective experience is seen as emerging from the physical substrate. It's what happens when a brain processes information in a certain complex way.
So how are scientists trying to bridge that explanatory gap? What are the leading theories?
Well, one major contender is Giulio Tononi's integrated information theory, or IIT.
IIT.
IIT proposes that consciousness isn't about specific materials or functions, but about the structure of information processing. A system is conscious, it says, if it has two key properties. High differentiation, meaning it can be in a vast number of different possible states. And high integration, meaning its parts are strongly interconnected and influence each other, lots of distinct states, but all working together.
And IIT tries to quantify this with a number.
Yeah, it assigns a value called phi A. The higher the phi value, the more conscious the system is supposed to be. It tries to make consciousness a measurable property of complex integrated systems.
Interesting. What's another approach, maybe from a more evolutionary angle?
That would be something like Michael Graziano's attention schema theory.
Attention schema.
Graziano thinks about it like an engineering problem. The brain is processing this overwhelming flood of sensory data constantly. To manage it, he argues, the brain has to build a simplified model, a schematic, of what it's currently paying attention to.
Like a user interface for its own focus.
Exactly. So when you see red, your brain isn't experiencing some mystical redness. It's accessing its internal model, which describes the properties of its current attentional state regarding that apple as simply red.
The conscious feeling is the simplified model.
That's the idea. It's a useful, quick, and dirty summary. Graziano points out that if our ancestors' brains were consciously aware of every single photon hitting their retinas, every muscle twitch, they'd be paralyzed by information overload, swiftly eaten, as he puts it.
So consciousness is adaptive because it simplifies. It gives us just enough information to act effectively.
It's a schematic representation the brain makes of its own attentional state, sufficient for survival. The feeling is the brain's description of its own complex processing. Hashtag tag 3.2 free will and liberated behavior.
Okay, whether consciousness is hi-fi or an attention schema, the brain is still fundamentally a physical system, made of particles obeying physical laws.
Absolutely, governed by cause and effect, from the quantum level up.
Which brings us right back to that huge philosophical battleground, free will. If every action is just the result of prior physical causes, how can we be free? Aren't our choices predetermined?
Are we just puppets? Playthings knocked to and fro, as the sources put it. It feels like a direct conflict.
It does. If physics dictates everything, where does choice come in?
This is where we have to be really careful with definitions. The physicalist view, which underpins most of modern science, has to accept there's no transcending of physical law. Our brains, our decisions, are part of that physical unfolding.
So if you could rewind the universe and play it again, the same choice would be made every time.
Given the exact same starting conditions, yes. The outcome is determined by the physics.
That sounds bleak. Doesn't it undermine responsibility, meaning?
It certainly undermines the idea of ultimate origin, the idea that your choice starts purely within you, completely independent of all prior causes. That kind of freedom seems incompatible with physics. But, and this is crucial, accepting the physics doesn't mean we throw out the concept of freedom. Instead, the sources argue it leads us to appreciate a different, but very real and profound kind of freedom. Liberated behavior?
Liberated behavior. Okay, explain that. How are we liberated if our actions are determined?
Think about the difference between, say, a rock and a person sitting next to it. A tree branch starts falling towards someone nearby. The rock just sits there. It obeys physics, inertia, gravity.
Right, does nothing.
The human, however, also obeying the laws of physics, might see the danger, process the information, weigh the risks, feel empathy, and choose to leap forward and push the person out of the way.
The behavior is vastly different, even though both are physical systems.
Astonishingly different. The human system, because of its incredible complexity, its brain, its history, its learned values, its capacity for foresight, can generate a far wider, more flexible, more liberated range of behaviors in response to the environment.
So freedom isn't about breaking the laws of physics, but about the complexity of the system operating within those laws.
It's about the sophisticated processing happening inside the human system. When we talk about making a choice, deliberating, deciding that's real, that complex internal process is happening. It's just that the process itself is physically instantiated.
So we keep the language of choice and decision because it accurately describes the high-level function of our brains.
Exactly. We embrace the sensation of free will, which is the subjective experience of that complex deliberation, and we recognize the vast, liberated behavior that distinguishes us from simpler systems.
And critically, responsibility still rests with the individual, right? Because the decision-making machinery is in that individual.
Absolutely. The complexity that allows for planning, moral reasoning, and action resides within the person. That's why concepts like accountability, praise, and blame remain meaningful and necessary for society. Our complex minds are the source of our actions, even if those minds operate according to physical laws.
Okay, so we have this complex machine, the human brain, capable of this liberated, complex behavior. What's one of the first, most fundamental things it seems compelled to do?
Cut stories. Create narratives.
It seems absolutely fundamental. As soon as we have language and some evidence pushes that back, maybe over 1 million years, the capacity for it, we start weaving tales.
Think about the Epic of Gilgamesh. It's the oldest written story we have, right? Thousands of years old, and what's it about? Escapades with petulant gods, quests, mortality. Why?
Why spend precious time and energy when you could be hunting or gathering? Just making things up, telling stories.
The sheer amount of resources we dedicate to narrative, creating it, sharing it, consuming it, suggests it must have offered some serious evolutionary advantage.
What are the theories? Steven Pinker suggests stories are like mental simulator?
Yeah, an adaptive tool. They build up a mental catalog of potential situations and strategies. You hear a story about betrayal or cooperation or a clever trick.
And your brain runs the simulation.
Yeah.
You learn how to navigate that social dynamic without having to experience the danger firsthand.
Exactly. It's a safe, cheap way to gain experience about life's complexities. How to organize a group, deal with conflict, plan for the future. It preps the mind.
There's also the idea linked to social cohesion, maybe even gossip.
Right. Some anthropologists argue language itself evolved partly as a kind of vocal grooming to maintain bonds in larger groups where physical grooming wasn't feasible.
And stories are a super efficient way to share social information.
Who's doing what to whom? Stories reveal the intentions, beliefs, and likely actions of others. Understanding other minds is absolutely critical for cooperating in groups, which was key to our survival.
So storytelling helps us build models of other people's minds.
To refine those models. And this constant narrative construction might not even stop when we're asleep.
You mean dreaming?
Some theories propose that REM sleep, when we have vivid dreams, is the brain continuing this process, running simulations, testing social scenarios, consolidating experiences into narrative form to make sense of them. Hashtag 4.2 belief in religion. Okay, so we have this powerful narrative drive. As our intelligence grows, that basic impulse to explore and explain the world starts to morph into something deeper.
An urge to find meaning, to infuse experience with significance.
Yeah. The technician becomes the philosopher. We're not just figuring out how things work, we're asking why, especially when confronted with our own mortality.
And we see archaeological evidence for this search for meaning going way back, those ancient burial sites.
Kafsa, in Israel, 100,000 years ago. A child buried with deer antlers. Other sites with bodies carefully arranged, adorned with thousands of beads.
These aren't just practical disposals. They look like rituals, attempts to do something about death, to transcend it somehow.
An effort to ensure some essence, some significance, carries on. And the cognitive science of religion offers some fascinating insights into how formal belief systems might have emerged from this.
It's not necessarily that evolution selected for religion directly, but maybe as a byproduct of other useful cognitive tools.
That's a leading idea, yeah. Pascal Boyer talks about it being an evolutionary package deal. It emerges from mental systems built for other survival tasks.
Like agency detection.
Right. Our brains are strongly biased towards seeing intention, agency behind events. A rustle in the bushes better assume it's a predator or a rival than just the wind. That assumption saves lives.
But that system can get over-applied.
Easily. So when there's a flood, a drought, a lightning strike, big, impactful events without obvious causes, that same agency detector system might infer a powerful, unseen agent behind it. A god, a spirit.
It maps neatly onto our social intelligence, too, thinking about what these powerful agents might want, how to appease them.
Exactly. But it's really important to stress, understanding the cognitive origins of religious belief doesn't automatically invalidate its value or meaning for people.
We need to separate the literal claims from the metaphorical or symbolic function.
Absolutely critical distinction. If a religious text makes a literal claim about the physical world, say the age of the earth, and that claim conflicts directly with overwhelming scientific evidence,
then from a scientific perspective, the claim is false, full stop.
Right. Science is our best tool for describing the material world. But that's also not the primary function of religion for most people.
They're not looking for scientific explanations. They're looking for community, structure, meaning, comfort, a way to deal with suffering and death.
Precisely. When you interpret religious stories and rituals, poetically, metaphorically, symbolically, they offer immense value. They build community, provide ethical frameworks, give context to life's journey, connect people across generations.
Like reciting an ancient prayer, say, the Kaddish. You might not even understand the Aramaic words.
But the act itself, the shared history, the connection to generations past who said those same words in mourning that provides profound coherence and meaning, regardless of literal interpretation. It's about the human connection it fosters. And this deep human need for coherence, for meaning beyond the literal, finds perhaps its purest expression in art.
Yeah, why do we do it? Why spend so much effort creating patterns of sound or color or shape that seem to have no immediate practical payoff? It's pervasive cave paintings from 30, 40,000 years ago.
It baffles and transports us. What's the evolutionary angle here? One idea is linked back to sexual selection, like we discussed with storytelling.
Jeffrey Miller, Dennis Dutton art as a fitness indicator.
Right? Creating something beautiful, but non-essential. A complex carving, an elaborate song, a detailed painting requires skill, intelligence, time, resources. It signals you have energy and ability to spare.
Basically showing off your good genes and resourcefulness to potential mates.
That could certainly be part of it. But, like with religion, it feels like that doesn't capture the whole picture, does it? The profound feeling art evokes.
No, it feels deeper than just signaling.
Art also likely played a role in honing our general cognitive skills, exercising creativity, practicing symbolic thought, building social cohesion through shared aesthetic experiences. It supports the whole adaptive package of language and complex thought.
But the sources argue the real power, the nobility of art, is in how it communicates a different kind of truth.
A truth beyond logic, beyond facts. The writer, Saul Bellow, said art pierces the seeming realities of this world to show something more genuine underneath. It delivers megadoses of essential human experience.
It expands what we can know about existence, but not through analysis, through feeling.
Exactly. I love that quote from Yip Harburg, the lyricist. Words make you think a thought. Music makes you feel a feeling. But a song makes you feel a thought.
Ah, that's perfect. Art links the head and the heart.
It gives us this intuitive, emotional grasp of complex ideas and experiences that pure reason might miss. It provides a sense of order and meaning in the face of chaos.
And maybe, at its core, art is also about fighting back against that mortality we talked about at the start, a quest for immortality.
A symbolic immortality. Knowing the physical self will decay, artists across millennia, Sappho, Yeats, countless others, sought to create something lasting. To enter the artifice of eternity, as Yeats put it.
To leave a mark that outlasts the body.
Exactly. It's not cosmic immortality, not on the universe's timescale, but it's a form of longevity measured in the lifetime of human civilization. If the work endures, something of the creator's mind, their feeling, endures with it. A defiance of decay.
Okay, we've explored the human drive for meaning, story, belief, art as a response to our fleeting existence. Now, we have to zoom out. Way out, and confront the ultimate physical fate of the cosmos, according to the science.
The long-term forecast. Physical eschatology.
Yeah.
And the timescales here are just mind-bending.
Let's use that Empire State Building analogy again to try and grasp it. Each floor up is 10 times longer than the floor below. We're on floor 0, the present.
Okay. Our first major landmark is way up on floor 11. It's about 5.5 billion years from now.
What happens then?
The sun begins to die. It's been steadily fusing hydrogen into helium in its core for about 5 billion years already, another 5 or so to go. But eventually, the hydrogen in the core runs low.
Helium ash builds up. Fusion slows down.
And without that outward pressure from fusion, gravity wins. The core collapses inward, compressing and heating up dramatically.
Hot enough to ignite something else.
Hot enough to start fusing hydrogen in a shell around the now inert helium core. This shell fusion is incredibly intense. It generates way more outward energy than before.
Causing the sun to swell up.
Massively. It expands into a red giant. It will balloon outwards, engulfing Mercury, Venus, and almost certainly Earth as well. Our planet gets vaporized.
Not a gentle end for the homeworld. What happens to the sun after that? Does it explode, become a black hole?
Not massive enough for either of those. After puffing off its outer layers, the remaining core, now mostly carbon and oxygen, will settle down into a white dwarf.
A super dense stellar remnant. What holds it up against gravity now that fusion has stopped entirely?
Pure quantum mechanics, something called electron degeneracy pressure.
Ah, the Pauli exclusion principle.
You got it. Electrons are fermions, and quantum rules say no two identical fermions can occupy the exact same quantum state in the same place at the same time.
So as gravity tries to crush the white dwarf smaller and smaller,
the electrons basically push back. They resist being squeezed any further. It's an incredibly powerful quantum effect that stabilizes the star against collapse.
And then it just sits there.
And cools. Very, very slowly over trillions and trillions of years, fading towards absolute zero. A dying ember.
Okay, so stars die out. But even before the last white dwarf cools, the universe itself is changing dramatically. Floor 12, maybe a trillion years from now.
Yeah, this is when the effects of dark energy really take over.
This mysterious something that's causing space itself to expand faster and faster. Repulsive gravity.
We don't know what it is, but we see its effects. And the consequence of this accelerating expansion is profound isolation.
Distant galaxies are receding from us faster than light. How is that possible? Doesn't that violate relativity?
Good question. It doesn't, because it's not the galaxies moving through space faster than light. It's the space between us and them stretching faster than light. Think of raisins in an expanding cake.
So they effectively disappear over a cosmic horizon. We lose sight of them.
They pass beyond the cliffs of space. Eventually, the only galaxies we'll be able to see are the ones gravitationally bound to us in our local group, the Milky Way, Andromeda, and a few smaller ones.
Which will eventually merge into one giant galaxy.
Milkomeda, some call it. We'll be stranded on this single galactic island, in an ever-expanding, seemingly empty void.
And crucially, we'll lose evidence of the bigger picture.
We'll lose access to crucial cosmological data. The cosmic microwave background radiation, the afterglow of the Big Bang, will be stretched to wavelengths so long they become undetectable. Future inhabitants of Milkomeda might have no way of knowing the universe ever had a hot, dense beginning. Hashtag 5.2, the degenerate era in cosmic dissolution.
Okay, climbing higher. Floor 14, we're talking maybe 100 trillion years out. What's the universe like then?
The last stars, even the incredibly long-lived little red dwarfs, will have finally burned out.
So, darkness.
Galactic graveyards, burnt-out cities, populated with charred cinders, as one source vividly puts it, just the remnants. White dwarfs, neutron stars, black holes, drifting the cold dark. The degenerate era.
But even these remnants aren't permanent, are they? There's talk of matter itself decaying, proton decay.
That's the prediction from many grand unified theories trying to unite the fundamental forces. They suggest protons, the very building blocks of atomic nuclei, aren't actually stable forever.
They just have an incredibly long half-life.
Astronomical. Maybe 10 to the power of 38 years, maybe longer. But given enough time, and we're talking truly unimaginable timescales, now every proton should eventually decay.
Into what?
Lighter particles like electrons, positrons, photons, basically dissolving into radiation.
So even the white dwarfs, the neutron stars, they eventually just evaporate, dissolve away.
Over those immense timescales, yes, all structures made of normal matter would ultimately disintegrate into a thin, featureless soup of elementary particles and radiation.
And what about things held together by gravity, like planets still orbiting these dead stars?
Even they aren't safe. General relativity tells us that orbiting objects constantly radiate energy away in the form of gravitational waves, tiny ripples in spacetime.
It's a minuscule effect for planets.
Infinitesimally small. But it's not zero. Over truly vast timescales, maybe 10 to the 35 years, even planets will lose enough orbital energy through gravitational waves that their orbits will decay.
They spiral inwards.
Spiral into whatever remnant they're orbiting, the white dwarf, the neutron star, the black hole. Gravity eventually reclams everything. All structure dismantled.
So stars die, galaxies dissolve, matter decays, orbits decay. It seems like a bleak end. What about consciousness? Could thought somehow persist indefinitely in this decaying universe?
That's a fascinating question tackled by physicist Freeman Dyson. He treated a thinking entity, the thinker, as a thermodynamic system.
Meaning it has to obey the laws, especially the second law of thermodynamics. Thinking takes energy, generates waste heat.
Right. Any computation, any thought process inevitably increases entropy. That waste heat has to be dumped into the surrounding environment.
Okay, so can the thinker keep doing that forever?
Dyson's calculation was initially quite optimistic, surprisingly. He found that the thinker could, in principle, operate more efficiently by thinking slower and at lower temperatures.
The colder it gets, the less energy each thought requires.
Essentially, yes. Mathematically, he showed it might be possible for the thinker to have an infinite number of thoughts, using only a finite amount of energy, as long as it kept slowing down and cooling down along with the universe.
Wow. Eternal consciousness on a finite energy budget. That sounds like escaping the heat death.
It seemed like it. But there's a catch. A fundamental thermodynamic snag.
What is it?
To dump its waste heat, the thinker needs its environment to be cooler than itself. Heat only flows from hot to cold.
And as the universe approaches absolute zero,
the temperature difference between the thinker and its surroundings shrinks towards nothing. Eventually, the environment becomes too cold to act as an effective heat sink.
It can't get rid of the entropy it generates by thinking.
Exactly. The waste heat builds up. At some point, the thinker generates entropy faster than it can possibly expel it. Dyson concluded that thought itself likely becomes physically impossible, choked by its own waste products.
So even thought succumbs to entropy in the end. That's sobering.
It is. But there's one final, even stranger twist in the very, very deep future. Something that arises out of pure statistics in an almost empty universe.
Don't tell me it gets weirder.
Oh, it does. We're talking timescales like 10 to the power of 68 years. Basically infinite time. The era of the Boltzmann brain.
Boltzmann brains? What on earth are those?
Remember, the second law is statistical. Over truly infinite time, even incredibly unlikely events must happen eventually, just due to random fluctuations.
Like monkeys typing Shakespeare.
Kind of, but on a particle level. In a near-empty, high-entropy void, random quantum fluctuations could, theoretically, spontaneously assemble particles into any configuration,
including a fully formed human brain.
including a fully formed functional brain, complete with a lifetime's worth of false memories and sensory experiences, that just fluctuates into existence for a brief moment before dissolving back into the void.
That's disturbing. A brain that thinks it lived a life but never actually did.
Precisely. And here's the epistemological nightmare. If the universe lasts infinitely long and is mostly empty high-entropy space,
Statistically, shouldn't these random Boltzmann brains vastly outnumber brains like ours that evolved through the incredibly specific low-entropy path of cosmic history?
that's the terrifying conclusion. If you accept physicalism in infinite time, the overwhelming statistical probability is that you are more likely to be a fleeting Boltzmann brain fluctuation right now than an observer with a genuine past rooted in cosmological evolution.
It calls everything into question. Our memories, our science, the very observations we've been discussing.
It's a profound challenge to our understanding of our place in the cosmos. If the statistics say we shouldn't exist in the way we think we do, what does that mean? Hashtag tag outro.
Wow. Okay. We have gone from the Big Bang, essentially, through the formation of stars and life, the emergence of consciousness, our search for meaning, all the way to the ultimate heat-death proton decay and the bizarre possibility of Boltzmann brains.
It's the entire cosmic story, as science currently tells it. A story of physical laws playing out, leading from structure to dissolution. An indifferent universe following its rules.
Relentless birth, death, and decay, it seems. Almost nihilistic when you lay it all out like that.
But maybe the significance isn't in that final outcome. The universe doesn't care. The significance, the sources strongly suggest, lies in us, in our ability to witness it, to understand it.
Our equations, our theories, they have no value floating in a void.
Their worth comes entirely from the minds that can comprehend them. Our consciousness, this brief flicker of low entropy, allows us to step outside the relentless flow of time, reflect on eternity, and crucially, create our own meaning.
Through the very things we discussed, our stories, our beliefs, our art, our attempts to build something lasting, even if only on a human timescale.
That's the extraordinary gift, isn't it? We are these temporary collections of stardust, aware of our own impending doom, yet capable of contemplating the infinite and building this incredible symbolic heritage.
We use our complex minds to push back against the decay, to create coherence.
And think about this. Our scientific understanding, the laws of physics, thermodynamics, any advanced civilization elsewhere would likely discover these same truths. They're universal.
But our human narratives, our specific myths, our art, our philosophies,
Those are unique to us. They tell the story of our particular journey, our struggles, our values. So the final thought maybe is this. If humanity were to vanish and some future explorers stumbled upon the ruins,
the science might tell them what the universe is like.
but what parts of our art, our stories, our beliefs would we want them to find to tell them who we were? What meaning did we manage to carve out of this brief existence against the backdrop of cosmic indifference? That's something to ponder.